Good afternoon. My name is Silvia Casarotto and I work at the University of Milan. My talk is entitled TMS-EEG is sensitive to the brain's capacity for consciousness, a reproducibility study. Our brain is the engine of our actions, perceptions, feelings, and thoughts. To the extent that we produce a motor output upon a sensory input, we can say we are conscious. Conversely, when we lay in deep sleep or during anesthesia, we aren't conscious because we are unresponsive and disconnected from the external world, and upon awakening, we do not provide any conscious report. However, in some conditions, we can be conscious and unresponsive at the same time. This occurs, for example, during dreaming and ketamine anesthesia. In these conditions, in fact, we appear as unresponsive to an external observer, but upon awakening, we can provide vivid description of a weird conscious experience entirely produced within our brain. Now imagine to have a severely brain-injured patient. Because of lesions, this patient could be impaired on sensory input or motor output, or both sensory and motor pathways. How can we say whether the patient is conscious or not? This time we have to open the black box. But what to measure? There are several theories about this. But the rather common feature across theories that has been identified as important for consciousness is complexity of brain activity. That is, the brain's capacity to process information in an integrated manner. So let's start from this theoretical prediction. To the extent that functionally specialized brain regions work in synergy to integrate information across highly specific functional networks, thalamocortical networks, we are conscious. How can we evaluate whether the brain is actually working like this in a conscious individual? By combining transcranial magnetic stimulation and electroencephalography. That is, by recording the overall electrical brain activity evoked by a focal, non-invasive, and direct perturbation of cortical neurons with TMS. If we imagine to stimulate a node of such a network, we will obtain a local activation that travels towards distant sites and produces secondary activations with highly specific temporal dynamics. In this case, we are conscious. If because of physiological, pharmacological, or pathological reasons there is an imbalance towards loss of integration, the network becomes modular. So stimulation of a node of such a network will produce a local, simple and slow activation that does not travel elsewhere. In this case, we say does not allow to sustain consciousness. On the other side of the spectrum, if the imbalance is towards loss of differentiation, stimulation of a node of such a network will produce a global and stereotypical activation that spreads like wildfire. Also in this case, we say that consciousness cannot be present. These theoretical predictions turned out to be true when looking at EEG responses to TMS recorded in healthy awake subjects during disconnected consciousness, such as dreaming and ketamine anesthesia, and during unconsciousness, such as during deep non-REM sleep and propofol midazolam xenon anesthesia. But in order to make all this clinically useful, we have developed this Perturbational Complexity Index, PCI, PCI is a real number between 0 and 1 that can be derived from EEG responses to TMS. And this number measures the complexity of the spatiotemporal pattern of cortical activations significantly evoked by TMS. From the distribution of PCI values measured in a large benchmark population, we derived an empirical cutoff, PCI star, that discriminates with 100% sensitivity and specificity between unconsciousness and consciousness, even if disconnected. Now, what happens if we apply this empirical cutoff PCI star to the distribution of PCI values measured in severely brain-injured patients with disorders of consciousness? Let's start from minimally conscious state patients. These patients show minimal signs of purposeful behavior fluctuating over time. As you can see here, almost 95% of these patients is correctly detected by PCI, showing that PCI is extremely sensitive to minimal signs of consciousness, which are visible from behavioral evaluation. What about vegetative state patients? These patients are able to perform reflexive movements only. Well, according to PCI, this rather homogeneous clinical category can be further stratified into 3 subgroups. We have no response patients with PCI equals 0 who show no significant EEG responses to TMS. At the population level, most of these patients have anoxic etiology and show voltage-suppressed EEG background. Then we have low-complexity patients who show slow and stereotypical EEG responses to TMS. PCI value of these patients is below the empirical cutoff. Finally, and most importantly, we have high-complexity vegetative state patients who show complex EEG responses to TMS with PCI values well above PCI star. Now, this neurophysiological stratification of vegetative state patients has clearly ethical and therapeutic implications. And also, concerning the outcome, you see that no response patients have a worse outcome as compared to high complexity patients. So all these results are very nice and promising, and we would like to promote the application of PCI in the clinics for diagnosis as a prognostic marker and to longitudinally monitor recovery of consciousness in patients. But to do this, we need first to further confirm and replicate these nice results in larger patient populations with different etiology, different brain lesions, and across clinics. This is what we are doing within this project funded by the Italian Ministry of Health. This project involves 2 clinical institutions in Sicily with patients with disorders of consciousness. This is the TMS-EEG equipment we are using. I want to underline that this equipment is different from the one used in the previous validation study. So far within the project, we have collected TMS-EEG data in 5 patients only. Well, the project just started, and because of pandemic, we had to temporarily suspend the recordings. But we hope we can restart soon. All these patients were vegetative state patients, meaning that they could perform reflexive movements only. All of them except patient number 5. In this patient, it was possible to observe sometimes the capability of fixating an object. Fixation per se is considered a minimal sign of consciousness, but in this patient, it was very difficult to assess this capability. and it was not present all the times. And therefore, I must say that diagnosis for this patient is really borderline between vegetative state and minimally conscious state. What does PCI tells us about the consciousness state of these patients? Patients 1, 2, and 3 show PCI equals 0, with a flat EEG response to TMS. Patient number 4 shows a slow and stereotypical EEG response to TMS with PCI value below PCI star. Patient number 5 shows complex EEG responses to TMS with PCI value well above the empirical cutoff PCI star. Now we can conclude that in this rather small sample of patients, we were able to replicate the neurophysiological stratification of vegetative state patients described in the previous validation study. This successful replication has been obtained using a different TMS-EEG equipment and including patients with metabolic etiology who weren't present in the previous validation study. Last, as in the previous study, no response patients have a prevalent anoxic etiology and typically show a voltage-suppressed EEG background, whereas low and high complexity patients show a more preserved EEG background with faster oscillations and larger amplitude. Thank you very much for your attention.